Okay, so today, this afternoon, we're going to start with Natal Oliveira da Costa. He has a master's degree in philosophy at UTS, and the rotation will be exponentialism has no close, where it might borrow some. So, Natal.
Thank you, Rafael. First of all, let me say thanks to the organizing committee, especially the organizing general, especially Dr. Faitelson for all the support, all the guests for the Latin American philosophy community. We really appreciate the support. As my somewhat provocative title suggests, in the first part of my presentation, I will argue that explanationism, which I will argue in a moment, I will define it in just a moment, has not much going for it. To be more specific, I will argue that in light of the debate that started back in 2013, we have reasons, or to put it another way, we don't have compelling reasons to accept this thesis, no matter how attractive it may seem. And in the second part of my presentation, as it's just too easy to find the holes in others' arguments, I try to be a little bit more constructive. And I will try to suggest a different way in which we can make sense of our intuitions beneath the idea of explanation. But what do we mean by explanation? Kevin McKay and Ted Boston, in a recent contribution to the hotly read book of the philosophy of Athens, put it in the following way. Do we get evidence for P by simply, and here's the simply is a very important word in the sentence, by simply realizing that P, if true, would explain some data? Explanationists answer this question affirmatively, maintaining that explanatoriness is evidence of truth, with various qualifications. And there are, of course, a lot of varieties of explanationism. According to the taxonomy that became canonical from Williams Lycan, he distinguished between 4 types of explanationism, depending on how one takes inference to the best explanation to be, to how fundamental one takes inference to the best explanation to be. Just to give an example, Gilbert Harman's famous paper that introduced the idea of inference to the best explanation to the literature in 1965, it would be, according to Lycan's taxonomy, what he calls ferocious explanationism. Because, according to Gilbert Harman, even enumerative induction can be reduced to inference to the best explanation. But we will, in my presentation, we will focus on the weakest claim, which is called weak explanationism, which is the idea that explanatory inferences, inference to the best explanation from a given set of premises, can epistemically justify a conclusion, and nothing more than that. It's prima facie very plausible, a very plausible thesis that this is judging by the way in which we use, both in English and Portuguese, the verb to explain. To give just 2 very prominent examples, we see Charles Darwin in the 6th edition of the Origin, and he says, for example, it hardly can be supposed that a false theory would explain in so satisfactory a manner as does the theory of natural selection the several large classes of facts above specified, would explain in so satisfactory a manner. In the same way, Albert Einstein says that the ability of the theory of relativity to explain the Mercury's perihelion in a qualitatively and quantitatively way explained is evidence again for the truth of the theory. Explanationism comes with a lot of promises. If you just skim to the literature, you see that, for example, there are philosophers that believe that it can help us to with an answer to philosophical skepticism, for example. In just a very small sample of the literature. Another thing for which inference to the best explanation has been put to use is in the defense of scientific realism. You should believe maybe in quarks, electrons, and other non-observables because they constitute the best explanation of the given evidence. And we can find also authors arguing that explanation can help with the problem of the priors for those who take this fact to be a problem at all. But in spite of all these promises, some authors have for a long time perceived that there is at first sight a tension between what our best theory of how evidential support works, Bayesian confirmation theory, and what explanation says. Basil Frassen, for example, in Law and Symmetry, argues that at least if we conceive of explanation as inference to the best explanation, as giving us reason to give a bonus credence to a given hypothesis based on how good of an explanation it is, it opens the agent up to a Dutch book. You will be incoherent according to the axioms of probability. But it's true though that it's not an argument against weak explanation, because as we saw, it's not committed to how the explanatory considerations are relevant, but just to the fact in general that explanatory considerations are relevant. And even if the person takes this idea that inference to the best explanation has to imply that you give a bonus to a hypothesis, even in this case, maybe the objection is not fatal, it's not the end of the conversation, because we have, for example, most prominently, Igor Duvan. He has defended for a couple of papers for some years now that if you give a bonus to the hypothesis, but at the same time you give a penalty to the rival hypothesis, you can keep the coherence in the probability distribution. But of course,
does Bayesianism ever intend to explain or just to increase evidence?
Yeah, as
that's an important point.
Yeah.
Increasing evidence does not necessarily lead you to explanation.
I'm not sure I follow what you say.
If you're increasing or you're revising your belief or increasing evidences, does it go necessarily towards the explanation?
Yeah, but I think that the commitment, at least of weak explanationism, is not that you will invariably get to an explanation. I think it's uncontroversial. The thing that is under dispute is the idea that the explanatory character of the hypothesis in itself is evidence for the truth of the hypothesis. The fact is that back in 2013, Elliot Sober and William Roche have published an article that sparked a debate that I believe reviews that explanationism has no growth. The title is very suggestive. Explanatoryness is evidentially irrelevant, or inference to the best explanation meets Bayesian confirmation theory. What Elliot Sober and William Roche actually argue is that the explanationist is committed to an inequality, in the sense that the probability of H given the observation and the explanatory claim, and what is the explanatory claim? As we see in the first slide, that H, if it true, would explain the data, must be higher than the probability of the hypothesis given only the observation. And what they say is that what is actually true instead is an inequality, because the data, the frequency data in the example I'm about to describe, screens off the explanatory claim from the probability. Though it is very ingenious, it's very clever, the example they advance. Back in 1950s, when we first noticed that there was a correlation between smoking and lung cancer, we were not sure that it was actually, there was a causal direction, right? Roland Fisher, for example, said that it could be in principle the product of a gene, of a common cause. Both things, both methods, so to speak, smoking and cancer would be a product of an uncommon gene. What Elliot Sober and William Roche argue is that in this sense, if we take, for example, that the probability that a given subject smoked, say, 10,000 cigarettes before he was 50 years old, given that he has lung cancer, is the same whether smoking actually explains causes and explains the cancer or not. Even if it were just a product of both things of a common cause, the probability would be the same. So they argue the explanatory claim, again in the sense that age would explain the data, cannot be in their sense explanatory relevant. There are basically, with some aside remarks, 4 answers in the literature at this point. Of course, all that I can provide here, given our limitations of time, is a 10,000-foot view, right? I don't expect you to be persuaded by my argument, but at least that if you, like me, suspect that explanation has no close, at the end of the presentation I hope to have given you some evidence in this sense. The 4 types of responses that the philosophers have presented to the challenge, to the so-called Isquinov challenge, are a response having to do with the notion of resilience that we are about to see, a response that was proposed both by Mark Lang and by Poston and McCain, having to do with the idealization of logical omniscience, and also about the necessity of explanatory considerations for inductive projection, and for a lack of a better word, the proposal of Mark Lang that I call explanatory types. But what do we mean by resilience? It goes back to the notion of weight of evidence that was first articulated by Keynes in his treatise, later Skirms in the 80s connected to the notion of resilience. There is a very nice article that, by the way, we went through with the help of Brendan, from James Joyce, by James Joyce. And what is the idea? I think it's, given our limitations of time, it's better to explain it with an example. What do we mean by resilience? Imagine that you have a coin. Most of the coins that you have acquainted you with were, in your life, were fair coins. And you don't have any reason to think that this particular coin is not fair. So we will assign, it seems reasonable to assign a credence of 0.5 to the coin being that will lend heads, for example. But consider an alternative scenario in which you have witnessed that the coin was tossed 1 million times, and about a half of the times it lent heads, and the other half of the times it lent tails. In both cases, you will assign the same probability, 0.5. But it's clear that in the second scenario, you have a much more robust basis on which to make this assignment. As a consequence, your credence is more immune to change, so to speak. And that is the idea that Ted Poston and McCain are saying that is done by explanatory considerations in this article. They say that we contend that under the conditions Roshan Sober provide, the explanatory claim increases the subject's strength of evidence, even though it does not affect the relevant first-order probability. And they give an example. They say that there is a urine, and that 2 people, Tom and Sally, just know that there are 1,000 X spheres inside the urine. The difference is that Sally knows that the X spheres must be stored in exactly equal numbers because of their atomic structure. Otherwise, they will rapidly decay and explode. They both witness 10 random draws, of which 5 are blue and 5 are red. What is the probability that the next random draw of the urine will be red? The next ball will be red, giving it a random draw. Both will say that it's 0.5. But what Ted Poston and McCain say is that actually, in spite of this, they will do the same assignment. The fact is that Sally's credence is more resilient because he has an explanation for why they have to keep this proportion. Otherwise, the X spheres would, in this fun toy example, explode. But what is the problem that I have with this response? Does the argument work? look at what they say. Sally and Tom have the same background evidence, except for this difference. Sally knows that blue and red spheres must be restored in exactly numbers. But remember, what was our explanatory claim? Is that H, whatever the hypothesis is, if true, would explain that. So this example would be a very good argument in favor of this idea that explanatory considerations make the agreements more resilient. If what Sally knew was that if it's true, the story about the decay would explain, but it's not what she knew. What she knows is that it's in fact the case. And so it's something that we could explain, for example, because one has more information than another. It's no mystery that they will have different epistemic attributes. Knowing that P, if true, would explain such and such, is different from knowing that P in fact explains such and such. The second, logical omniscience, is actually one objection that Elliot Sober and Roche themselves anticipate in their first article. It might be suggested that the spin-off test that we have used for confirmation relevance is misguided. Consider proposition I, which says that O logically implies H. Surely I is confirmationally relevant to H. If you know that O is true, but don't know that O implies H, and then you learn that it is logical fact obtains, that would have an impact on how confident you are that H is true. What Sober and Roche say about it? The reason this inequality is true is that purely logical and mathematical explanations are baked into probability functions. And so, McCain also say, if knowing these explanatory facts amounts to knowing some probabilistic relations between a hypothesis and evidence, then this response fails. And it seems plausible that William Sober, Elliot Sober and William Roche are assuming that if we drop the idealization of logical conditions, or to put it different, for agents like us, explanatory considerations are in fact relevant. But I am skeptical even of this claim, because again, what is the explanatory claim of weak explanations? Is that H, if it would explain. Whatever explanatory considerations may mean, it seems that it has to do with the explanatory goodness of the hypothesis itself. But in our example, the fact that O entails the hypothesis is a characteristic, is something about the evidence and not about the hypothesis itself. Klein-Hager has defended this proposition that actually the explanatory considerations are not just relevant, but they are actually indispensable. Okay. He actually first targets a slightly different spin-off challenge, and he says the following: say that there is an explanatory connection between two phenomena X and Y, if and only if at least sometimes X causes Y, Y causes X, or X and Y have a common cause. Let C1 be the hypothesis that the smoking causes cancer, C2 the hypothesis that cancer causes smoking, and C3 the hypothesis that they have a common cause. Then the negation of C1 or C2 or C3 is the claim that there is no explanatory connection between smoking and cancer. And that is what I found is problematic in his response, because it's far from clear to me that, for example, Sober and Roche would deny that the absence of this relation, the negation that there is any causal connection between the claims, the variables, is explanatorily irrelevant. But it touches at a more fundamental problem, a distinction that many times has not been made in the literature, in the literature of that explanation, but that we found on the literature, on the nature of the scientific explanations that unfortunately have developed largely independent of each other. That is the difference between an explanatory episode, an explanatory fact, is the thing in the world, so to speak, doing the explaining, and the explanatory vehicle, which is what according to inference explanation, should be irrelevant. The final proposal is from Mark Lane, is the idea of explanatory types. He says, why became a special province in a theory of confirmation to always being O's best explanation? The answer is that background opinions about the kind of explanation that some known fact is likely to have are an important sort of background opinion. There is a better example of his proposal in Delson's recent Cambridge element, and goes like this. Imagine that your remote control stopped functioning. It's more probable, it seems reasonable to suppose that only one thing, whether it's a battery, whether it's something with the button, that is stopped to work, and not that multiple things happen at the same time. And he says that is the case because we have this explanatory type of electronic things, so to speak, that they usually, when they stop to work, it's because of one part of the device. What I think is that actually, again, just like the other proposals, doesn't seem to vindicate, at least to my mind at this point, the explanatory claim, but ironically, it seems to vindicate a proposal that was largely neglected by Richard Feynman, who says that explanatory reasoning, at the end of the day, is not a third type of explanatory of inference besides deduction and induction, but that it's actually anti-means. That what we have in the so-called explanatory reasoning are actually implicit premises that are always reducible to combinations of deduction and induction, says Richard Feynman. In the case of we see footsteps on the beach, what is more probable, that a human being passes or that a cow wearing shoes passes by? He says that the first one is to be preferred not because it's more simple or any other explanatory version, but because of the implicit premise that in the vast majority of non-case, footprints are produced by man. Again, just simple and unrelated deduction. And I think that Lane's proposal can be reduced to it. Finally, I don't know how many minutes I have, but what good is an explanation? I think that, as I mentioned, both programs, Inference to the Best Explanation and the nature of scientific explanation, have unfortunately developed largely independent of each other. And the much needed approximation can help us make sense of a sense in which explanatory considerations are relevant and that it's more modest but makes more sense. It has appeared in the literature what has been called understanding first view, the idea that instead of taking explanation as the more core and important principle, we put it in the background and put it instead the notion of understanding as more core. But maybe you are wondering, but understand, are we not just exchanging a poorly understood concept by another that is even more subjective and ethereal? But they have a very specific explication of understanding. That is the ability to draw counterfactual inferences. It has some attractive features. It can account easily for the graded nature of understanding, different from knowledge, for example, that it's a matter of on-off. You have knowledge or you don't have. You have more understanding. It seems to make sense. And the more counterfactual inferences you are able to make, more understanding you have. It accords with the way in which we test for understanding. For example, when we apply a test to students, and we want to know if they really understand what we are, most of the time, trying to make them think beyond the specific cases to counter-affective situations. It's comparative probability view of explanatory goodness from Lipton, and it accounts for the role of idealization and model-based reasoning, Newtonian mechanics. It's false, but it allows for understanding, because it allows to do a huge number of counterfactuals. My last slide is that the explanationists love that first quote that I mentioned about Darwin, that a false theory would explain in so satisfactory a manner. But we have a lot of this vocabulary about explanation in the origin. For example, we have only the word inexplicable. Darwin uses 20 times. It would be inexplicable otherwise, according, for example, to the independent creation hypothesis. And I think that this notion of understanding first view of explanation help us make sense of it. Explainable. The differences in the anatomy of fossils in the geological layers say X and Y. Consider the first explanation. They are the product of a long process of natural selection. For the sake of simplicity, let's put aside things like genetics, drift, and other causes of evolution. And explanation 2, they are the product of multiple divine acts of creation. Why the first one is a better explanation? According to this understanding first view, it seems to me this is the fact that in the first case, we are able to draw counterfactual inferences. And in the second, we are just not. Imagine that, for example, we are comparing two geological layers, and according to the first hypothesis, if we say, had we instead looked at another, whether it's above or below layer, what would we have found? Maybe it's difficult to say precisely, but we have an idea, because the mechanism of natural selection sets constraints on what we can expect. And on the other hand, the divine acts of creation, anything is possible, anything goes, right? So HF2 would provide us with more understanding, there is would enable us to draw more counterfactual inferences. Thank you.
Thank you, Nathan. Now we're open to questions. Brandon?
Thank you. That was great. Here's another maybe way for Bayesian to do it. I mean, I agree with what you're saying. It's weird to put this additional content, right, and then ask what effect that has. But here's a different way. There's all this literature on causal modeling, Bayesian causal modeling. Why not the following understanding of this? Sometimes when you intervene on a variable, that raises the probability of something else more than just conditionality. And why not just take that to be what it means for there to be explanatory over and aboveness? So it's not part of the content, it's a feature of the causal model.
Okay.
And I think that's immune from the SOA rejection, certainly.
Okay. It nonetheless, it doesn't say weak explanations in the way they describe it.
Because I'm offering a different explication. Here's what it means to say. X, if true, would explain. It means when you intervene as opposed to merely conditioning. That makes more of a difference than just merely conditioning. I'm offering an alternative explication. Not as a content, but as a feature of the models, the causal models themselves.
Yeah, I will have to think about that. Thank you.
Any more questions?
Well, I think that explanations play multiple roles. One of them is subjective, which is maybe it's a predictive model that makes sense to us. The other is objective, which would be a predictive model that captures causal and metaphysical relations. And so it allows us to understand counterfactuals. This causation, usually understanding a causal structure involves knowing a lot about counterfactuals. And the third thing I think explanation is about is a heuristic. Because we say that we want to select the best explanation. And the criteria we use, I think, are heuristics, which is simplicity, lack of ad hocness, and unification. And so it's a big topic.
Yeah, of course. If I got you right, inference to the next explanation would be something like an heuristic to Bayesian reasoning for limited agents like us, right?
Yeah.
Yeah, this very proposal was advanced by Samir Lógica in 2001. It's very interesting. Yeah. Oh, just one thing, if I add, is that one problem that some people will take with this view of understanding first view, is that it's perhaps too much context sensitive, because what counterfactual inferences you can draw depends on what else you know, right? So people have introduced, for example, the idea of the epistemically well-situated science, for example. But I think that at least for a subjective Bayesian perspective, that really accepts this, the fact that the background conditions, the epistemic standard that each one of us carries, plays a real difference. It's not actually a bug, but a feature of the proposal, right? But thanks.
Okay, so we're out of time. Let's
Okay, fine. So first, I want to make it known that I'm just an undergraduate student. I have already finished my undergraduate degree. This is the first time I'm modeling. So I want all the feedback that you can provide because I'm planning to present this model as my writing sample when applying to a PhD. So yeah, no mercy, please. I want criticism. So yeah, I will talk about. The title is kind of clickbait because I'm not adding anything new to the basis of the algorithm that is conditionalization. I'm just putting some external constraints on the model. So I will set the agenda. I will start giving some motivations for this model. I'll let you know my background is in philosophy of cognitive sciences. So most of the things I read about are philosophy of mind and traditional epistemology. So the motivation will be very guided by consideration from the philosophy of cognitive sciences. So I will remain neutral regarding rationality at least until the end of the presentation. I know people love rationality and the event is called RatioLog, but if you want me to talk about...
We don't like, we don't move, we try to understand.
Okay, yeah, you're trying to understand. If you want me to talk about rationality, I can do it at the end of the presentation. But probably I won't have time to do that. So let's start with the motivation. So there is a philosopher of mine that is called Eric Manuel. He's like a son of Jerry Fowler. He loves the hypothesis of the language thought, and his main purpose in his whole career has been to defend the language thought hypothesis. So he makes a claim against Bayesianism in cognitive science, and a descriptive kind of Bayesianism. And he points to certain effects that have been found in the literature of cognitive science that are called doxastic resistance effects. And these are these three effects. So first of all, we have found that there are a lot of cases of learning blindness. What I mean by this is that we usually fail to update on pieces of evidence that are available to us. That doesn't seem really rational. There are cases of political perseverance. So even after receiving a piece of contrary evidence against an attitude we have, that attitude might remain unchanged. Yeah, that's something that has been found in the literature of cognitive science. And finally, belief polarization that I will characterize as the following. When we confront equivocal evidence that P and evidence that not P, our attitudes might reinforce in the direction that they already had. before confronting these evidence. So all these effects seem pretty irrational, at least for an intuitive reader. So I won't claim anything about rationality, but I will try to explain why these effects occur without making any changes in the Bayesian algorithm. So this is the argument that Manuel makes against Bayesianism in cognitive science regarding belief of data. So the main premise is the second premise. He says that if we have a tendency of learning blindness, belief perseverance, and belief polarization, then the belief of data has properties that no Bayesian algorithm would ever instantiate. All right. So in a few words, the argument is saying that stochastic resistance effects are inconsistent with the belief of data being Bayesian. And well, there are responses to this argument. Actually, probably a lot of people know the work by Kevin Dorst, where he tried to rationalize belief polarization. There are other works by other people that explain that if the agent has certain stochastic attitudes, for example, the belief that the source of information is untrustworthy, you might have something like belief perseverance or even belief polarization.
What did you just say?
Oh yeah, and the belief that the source of the information, the source of the evidence is not trustworthy.
Okay.
Yeah. If you have those kind of attitudes, you might expect these effects. And there is a more recent work by, I don't know the name of the author, but he posits some networks of beliefs that resemble Lakatosian research programs. I don't know if you're familiarized with Lakatos's work. So there is this idea that you have some core hypotheses that are like protected by a belt of hypotheses that are really easy to revise. So these core hypotheses remain unchanged even if you find counter evidence due to the protective belt of beliefs. So if you have these kind of attitudes or these particular networks of belief, you can expect belief perseverance and even belief polarization. But those models cannot explain learning blindness. And actually, this kind of response expects a lot of particular stochastic attitudes, and I want a more general response than that. So my model will try to give a more general response to why these effects might happen. All right. And another reason why I'm modeling what I will show you is that I think there is some bias in the literature on Bayesian belief acquisition. They all focus on belief of data, and that's not the only process that matters when we acquire beliefs, when we form beliefs. So I will make a move that has been happening recently in epistemology, that is going beyond beliefs and credences. I want to pay attention to other parts of our stochastic and epistemic lives that are more active. We inquire, we wonder, we make questions to the world. I mean, we just not receive evidence. We just not update on evidence that we passively receive. We do things to pursue evidence and answer our questions. And it's important to notice that the world in general produces far more potential evidence than we can take up. I mean, there is a lot of information surrounding us. So there is a computational need for discrimination among pieces of information that deserve to be processed by data. And that's the functional role of attention. So my presentation will focus on the stochastic attitudes. I love beliefs, I love credences, I love traditional epistemology, but I will focus on attention. So that's what I'm going to try to do. I will try to formalize the attention cognitive process. And I will argue that if we introduce attention to our models of belief acquisition, we can explain easily this phenomenon of stochastic resistance. So I will start with the model. Fortunately, yesterday Brandon has already introduced us to the probability calculus. So I will start with characterizing the credences of the agent. Let L be a set of propositions that is composed by atomic propositions and the composite propositions that emerge from applied directives and positional rules from propositional logic in the basics. This function from here will map propositions from this set to real numbers that represent the credences of our agent at time t. So what I'm stating here in these three first constraints is just that the credences of the agent will follow Colorado's axiom. So in other words, the credences of the agent might be represented in a probability table. That way is the constraints that Brandon has already mentioned this already. And I'm adding an update rule that is standard conditionalization. That means that the agent changes her credences from time to time according to this definition of conditional credence. That's all I'm assuming. I mean, this is pretty basic stuff. So the agent will have credences. And I'm also working with beliefs, full beliefs. And here is something that might be controversial because I think there is a lot of people that don't like the Lógica thesis. I like it, but if you don't like the Lógica thesis, the model can still work without full beliefs. You can still work with just credences. This is just I want to do. So we will have a function, b sub t, that maps propositions to the set of 0 or 1. If the function maps a proposition to 1, it means that the agent believes the proposition. And if it maps to 0, it means that she doesn't believe the proposition. That's all. And the rule for full belief will be the Lógica thesis. That means that the agent believes in a proposition B if and only if the credence in that proposition is equal or greater than the threshold. That's the Lógica threshold. Alright? So the threshold must be greater than 0.5 and up to 1. And well, from the way credences behave and the Lógica thesis, we can just derive another diachronic rule that is Lógica based. So the agent will update her beliefs according to this condition. The conditional credence given the evidence should be greater than the Lógica threshold. So that's nothing new. Until here, I have to say nothing new for the Bayesian model. So the original part is this one. So I will formalize attention the following way. So there is a lot of literature on attention. Actually, even though it has been just recently introduced in the philosophy of normativity and epistemology, the philosophy of mind has already been talking about attention since last decade at least. And in cognitive science, it's easier to study attention than beliefs because we have like eye tracking models, so that's easier to study empirically. So I'm following some philosophers that have offered a summary in the philosophy of attention. I'm mainly following these guys, Sebastian Batzel, that has a really cool book called The Structure in Mind, How Attention Shapes Consciousness. That's the title of my book. And that's a really good book. If you're interested in attention, you should read that book. So all these people agree at least in one thing. The functional role of attention is to prioritize pieces of information, or to deprioritize. So attention determines which pieces of information will fit some cognitive process. So attention works through our cognitive lives, not only regarding update. I mean, there is sensory motor attention, there is visual attention. Attention works everywhere in our cognitive lives. So I will focus just on attention that selects information for belief update. That's the only thing I'm working on. And the way attention selects pieces of information is by attributing salience. It's by how salient are pieces of information. So I will work following some previous contribution to formally represent priority structures by working with a salience function that maps propositions to the interval between 0 and 1. And there is a function that represents how the agent assigns salience to pieces of information at instant t. And then for any gamma sub t that is a finite subset of the set of propositions and represents the potential evidence of our agent, I mean the information that surrounds the agent. The set of pieces of information our agent will attend to at instant t, A sub t will obey the following constraints. So first of all, this is the set of attended pieces of information will be a subset of the potential evidence, of course. The agent cannot invent information. And this is the substantive claim. For every proposition in the set of potential pieces of evidence, that proposition is in the attention set if and only if it maximizes salience and it surpasses a certain attention threshold. You can interpret the attention threshold as how disposed the agent is to update on information. If the attention threshold is really high, it means the agent is really selective with the information she will take into account. If the threshold is really low, it means the agent is kind of liberal with the information she selects to fit the update algorithm. And well, this set will contain the total evidence the agent will process between an instant t and t plus 1, the next instant, if and only if the credence in the conjunction of every piece of information in the set is greater than 0. And I'm posing this constraint because, as you might remember from yesterday, so this is the definition of conditional credence. Sorry, I don't know if you can see. So do you remember the formula from conditional credence? Thank you. So is this one? The probability of E equal Q is the probability of the conjunction over the probability of the.
You don't want to join make them?
Sorry?
You don't want to join make them?
I forgot something.
No.
So this is the constraint. So if A sub t contains all the evidence the agent will update on, the credence on that total evidence should be greater than 0. Otherwise, she cannot update. Okay? That's why I'm using that constraint. That's everything I'm using. So basically, that's the model. That's my formal representation of attention. Well, until now we cannot say anything very substantive. So to show that the obsessive resistance effects are consistent with believably being Bayesian, I will evaluate what I will call attention policies. Because if you can see here, I haven't restricted the salience function. So I'm leaving that open because I want the model to be able to evaluate different attention policies. And by attention policies, I'm referring to salience functions, ways to attribute salience to pieces of information. So I will evaluate two attention policies, two functions attributing salience. And to start with that, first I want to define these variables, because if we are paying attention to an agent that has these capacity resistant effects, she might be kind of obstinate with her beliefs somehow. So to represent this behavior, I will talk about these two variables, that is the impact on credences and the impact on full beliefs, defined relative to a set C sub t that represents the core attitudes of the agent. Probably, you can interpret this as the most important beliefs for the agent, or the most important credences for the agent. So, I don't know if you are familiarized with quadratic distance measures. I mean, this is really common in Bayesian epistemology. It's employed to calculate prior scores and measures of inaccuracy and accuracy. So I'm not using it for normative purposes. I just want to measure how much is the impact of a potential piece of evidence E on this set of core attitudes. That's why I'm using this quadratic distance. All right. So we have an impact on credences and impact on full beliefs that is measured by this quadratic distance formula. So an obstinate agent might be characterized by either of these two policies. So first we have the policy of obstinacy regarding credences. So my first candidate to explain toxicity resistance effects is an attention policy that works the following way. The lower the impact in core credences, the greater the salience piece of information will have. So the salience function will be this one, minimizing impact on credences. And I have another candidate to explain this phenomenon, obstinacy regarding full beliefs. So the way this attention policy works is the lower the impact in core full beliefs, the greater the salience. So it minimizes the impact on full beliefs. Right? So I will show that this can explain toxicity resistance effects by a toy example. So let's imagine that we have an investor who owns a nuclear energy company. She's called Grace. And let G be the proposition that she is a good person. For the sake of the discussion, let's assume that there is a proposition that she is a good person. If you are an ethical anti-realist, you will probably have problems with that, but let's assume that. Let's see be the proposition that her company cares about the environment, and W the proposition that her company systematically throws radioactive waste into this. So we are describing the credences by this probability table. As you can see, she's really confident that the world is, this is the actual world. So she's really confident in that she's a good person, that her company cares about the environment, and that it is false that her company throws radioactive waste to the sea. So this is the current situation. Yeah, this is the current distribution of this agent, Grace. No, I'm just giving all her toxicity attitudes here. Yeah, that's all. Yeah. So let's assume that she updates these attitudes by conditionalization, and let's assume that her core attitude to fill my model is that she's a good person. That is to say that the set of core attitudes is just composed by G. Now, for the sake of example, let the Lógica threshold be 0.7 and the attention threshold be 0.8. Now, imagine that a source of information in which Grace fully trusts exposes her company for systematically throwing radioactive waste into the sea. That means that she has potential evidence W. Alright? That's what I'm saying here. The set of potential evidence includes W, just W. So we might ask ourselves, will Grace update her credences in this piece of evidence? Well, this depends on the way she attends the information. And I will evaluate both policies of attention. So first, if we assume that she is obstinate regarding credences, then we are assuming this. And the salience of this piece of evidence will be 1 minus the quadratic distance of the credence in G and the credence in G conditional on W. And this is approximately 0.7. So the salience of this piece of information is approximately 0.7, and that's lower than the threshold. So by the constraints of my model, that won't be in the set of attended pieces of information. Therefore, Grace will fail at a date. But that is correct. Okay. And we can do the same with the other candidate obfuscation regarding full beliefs. So now we are calculating salience this way, minimizing the impact on full beliefs. So the salience of this piece of evidence will be 1 minus whether she believes in G minus whether she will believe in G given W. And this is 0 because right now she believes she's a good person, but if she would update on W, she will want to believe that she's a good person. So 1 minus 0 is 1, and the second power 1 minus 1 is 0. Okay. So this is lower than the threshold. So again, by the constraints of my model, this piece of information won't be in the attention set. So Grace will fail to update on W. So that's the first scenario. I will finish with the second scenario. So now imagine another alternative. So in this case, two sources of information in which Grace fully trusts gave her equivocal evidence about her company systematically throwing radioactive waste into the sea. That is to say, the potential evidence includes both W and not W. This is the set of potential information that she can take to update on. So how will her attitudes change? Again, this depends on the attention policy she has. And if we evaluate obstinacy regarding premises, we will find that by the constraints of the model, she will update on the negation of W. She will conditionalize on the proposition that her company does not throw systematically waste into the sea. And therefore, the new occurrences will be these ones. And as you can see, if we go back to this current distribution, the ones that were greater than 0.5 now, in this case, they are reinforced. They are closer to 1, and the one that was lower than 0.5 now is 0. So this is precisely the polarization. And again, with obstinacy regarding to full beliefs, we can make the same calculations and determine that she will update on the negation of W. So again, the occurrences will reinforce on their previous direction. So I may finish with this. My toy example shows that the model predicts belief toxicity resistance effects, given that the agent follows one of these two policies, obstinacy regarding occurrences or obstinacy regarding beliefs. So I've shown that even if belief update behaves in a Bayesian way, if we have this external constraint of attention, the agent will exhibit these toxicity resistance effects. So belief update being Bayesian is not consistent with the findings in the empirical literature of atomic science. But well, my model can make many things. For example, I've managed to give some sufficient conditions for these effects, for learning blindness, for belief perseverance, and for belief polarization as well. But if I have got 5 minutes, okay. I'm just going to the concluding remarks. So I've shown that if we represent an agent's toxicity life as being characterized not only by belief update, but also by how she attends the business information, then toxicity resistance effects, belief polarization, learning blindness, and belief perseverance can be predicted, given some attention policies, obstinate attention policies. So this model predicts these effects without requiring any particular toxicity attitudes. And that's more general than the solutions that Kevin Lewis and these guys have already proposed. And the way these attention policies work, the ones I've been considering, obstinacy regarding belief and obstinacy regarding premises, is informed by insights from the cognitive science. I mean, core beliefs and core credences are really important for dissonance theory, which actually Manuel posits as an alternative for Bayesianism. So I'm showing that you can introduce dissonance theory in a Bayesian framework of belief acquisition. Additionally, if we restrict this set of core attitudes to be a set that only contains propositions about the self, for example, the proposition that I'm a good person, that I'm smart, and the like, then we integrate a really important part of dissonance theory and the cognitive experimental literature into a Bayesian picture of belief acquisition. So Bayesianism wins. And well, even though I haven't talked about rationality, we can use this very simple model to evaluate if an attention policy is rational by imposing additional constraints on the salad information. So yeah, that's all I want to say. These are references a lot. Yeah.
Thank you very much for that, Brandon.
That was great, really great. Just a small dialectical point, right? So Mandelbaum, he's not concerned really with rationality. He's making an objection to the descriptive adequacy of it.
Yeah.
So you don't need to talk about rationality this time. I mean,
Yeah.
and that's clarification, just a helpful clarification. you shouldn't even.
Yeah, I mean, this is descriptive.
Yeah.
It was not required to talk about rationality,
Right.
but I want you to notice that this model can be used for normative epistemology. Meaning, I've decided to do this because I've noticed that in epistemology, attention is now a hot topic, but it is not informal epistemology, not yet at least.
Well, there's Kathy Kwok, but that's
Okay.
the only person I know.
Okay.
But you should, I should introduce you, Kat, because she's organized.
Yeah, I would love. Yeah, definitely. So yeah, that's. Yeah.
Just very quickly, is there any new?
Yeah, but
Go ahead.
Well, you've been using this word attention that you claim to borrow from cognitive science.
Yeah.
But really what it seems that you're doing is just a theory of selective conditionalization with a bias for inertia.
Okay.
That seems to be what it is. It's not about attention. I mean, the
Okay.
person can look at counter evidence for a long time and pay attention to it, but fail to conditionalize because she has a bias for inertia, for what she already believes.
Okay. Well, I'm just following the literature, and attention is considered as a kind of informational gate.
Okay.
So even though if you are thinking about a piece of information, that doesn't mean you are attending it in a higher cognitive process.
Okay.
Meaning, so yeah, I mean, there is some sense in which you are attending to the information if you are thinking about it, but if you do not integrate it to your cognitive system, you are not attending it in this sense.
Okay.
Yeah.
And maybe somewhere you can use this idea of bias for inertia.
Okay.
Yeah, maybe it's helpful to clarify.
Right. Okay. I will take notes.
And there's a whole literature on algorithms that use this idea of inertia, momentum,
Okay.
second order momentum, all sorts of things. So if you start looking for these keywords, maybe you'll find interesting literature.
Okay.
Because neural networks, for example, when they're trained, there is a bias for inertia in the direction they're going in the train. So then maybe you're gonna find something.
Okay. Thank you. I will ask you for papers. Yeah.
No, we're gonna have fun this whole week. We're gonna talk a lot.
Yeah. Definitely.
Very quickly, it's not really a trouble with biasm. The trouble is its misuse.
Okay.
The trouble is misuse. It's like kind of behavior bias against using biasm.
Okay.
So yeah, in a sense, it's a kind of psychological side of rationality and not pure rational.
Okay.
That's the way I understand you always.
Okay.
I think it's worthwhile to separate misuse of something.
Right. Okay. Yeah. Somebody.
okay, so last question, Nick, and then we are out of time.
My comment is a request, and feel free to say no if it's too long. But could you briefly explain what are the alternatives, or what is the alternative that the original critics of the Bayesian framework proposed?
Yeah.
So be very brief because they're all.
Yeah. Mano talks about the immunological belief system. So he says that our reason is driven by this system of core attitudes that are really reluctant to change. So they are mainly from dissonance theory attitudes of ourselves. And the reason doesn't always based on rules, but it always rules that remain these attitudes unchanged. So, and they appeal to an affective state. So the beliefs are correlated with affective states. Mainly if you get a piece of information that it's a menace to these core attitudes, you will be in a negative affective state, and that will drive your reasoning. So it's kind of really emotional theory of the
But they do not propose a formal theory.
No, they
Ah, okay.
yeah.
Okay, thanks.
everyone for being here. So I have more slides than time. I will have to talk briefly in some of them. So this is my PhD project, and so it's very open yet, so I have time to reframe it and change. Everything started when I saw a lecture of Daniel Loic, which is a professor. He is a professor of Virginia Tech, and he mentioned this concept of fragmented mind. And it caught my attention because he mentioned consistency. So I started my PhD project here. So this is the table of contents. So the first slide is just a quote that I found very recently from Hans Teuber. And I will read here because there's a lot of quotes, so it's better for me here. So this for anxious people, this is the resume of my presentation. So I found this quote in a PhD thesis from MIT, and he says the possibility that the logic of Gibbsian systems set up for physical chemistry might be equally applicable to biological and social systems was considered more and more absolute. So I found this quote when I typed the content of my PhD project on a platform called Consensus to see if anyone was doing something related to what I want to research. I found 10 articles or papers about something similar that I was doing. Then I found this PhD thesis with this quote, which I think is very adequate for my work. So what does it mean, what he's saying? It means the interpretation of what he's saying is that the Gibbsian systems model interacting components via probabilistic dependencies, not deterministic laws. So Teuber saw potential in applying this logic to cognition, society, and science. So this is what I'm trying to do. Probabilistic graphical models, for example, Bayesian networks, Markov-Random fields, extend this framework to learning and inference. And Monte Carlo Markov chains methods simulate dynamic exploration of belief spaces, analogous to scientific reasoning. So this is an introduction. So my motivation, I will go very fast through this because there's a lot of slides here that are not that. So just to say what I'm interested in intellectually, so it's uncertainty and reasoning under uncertainty, non-sharp measures, rationality over probabilistic and statistical concepts, and non-classical logics. Those are my main interests. guiding questions because I'm going to go straight to the content. But let me just read this one. So my question is, can we model epistemic processes in a way that reflects how scientists and minds evolve? So I'm talking about philosophies of science and about how people think in terms of probability in statistics. So and so I'm going to skip this because it's too long. And go straight to the problems that I started to find in philosophy of statistics. This is a highly problematic field because there's many problems that happens with statistical data and studies. So basically people can die from a bad research and a bad interpretation or something like that, especially in medicine. So this is very important. So there's all kinds of problems. So the first one, we have high-level issues that are different methods and models. Which one is better, Bayesianism versus frequentism. And we also have very simple errors, like missing data, sloppy data handling, transcribing errors, and mistakes in arithmetic. This happens all the time. It's not that uncommon. Okay, so we had I sampled here in several medical papers that were retracted. So these things happen, you know. It's not just philosophy. These things are real problems. So, and we have problems inside the methods. No matter if they are a good method, no errors, we still have limitations of statistical adjustments. For example, confounding variables in observational studies. Another problem of philosophy of statistics is that the crisis in reproducibility and replicability. So when you take a study, replicability is when we make the experiment all over again, and the result isn't the same. This is very problematic and common. And reproducibility, when you recompute the data, you don't make the experiment again, but you do the statistical procedure all over again, and the results are not the same. So now I'm going to fragmented mind because this problems of philosophy of statistics maybe can be. When I started reading the book, which is collection of articles. No, the book is just a collection of articles about fragmented mind. Let me first explain what is unity and what is fragmentation on the mind. Then so unity, when you have a unity in the mind, you have consistency and closure. So agents have a unified representation of the world at time t, a single state of belief organized by two principles: consistency, the total set of an agent's beliefs is consistent, and closure, the total set of an agent's beliefs is logically closed. That is, agents believe the logical consequences of their beliefs, all of them. This is unity. And fragmentation. In fragmentation, it's different. So we have four conditions here for fragmentation. So the total set of an agent's beliefs at time t is fragmented into separate belief states. Each belief state is a fragment whose constituent beliefs are consistent with each other and closed under logical constants. So individually, they hold the principle of unity. But the belief states of a single agent are logically independent. They may not be consistent with each other, and the agent may not believe the consequence of his belief fragments taken together. Different belief fragments of a single agent guide the agent's actions in different contexts or situations. So you have many different belief states in someone's mind. That's the idea. So this is the main authors that I'm trying to be inspired by them. So Cherniak is very important because he introduced this concept mainly of comparative organization and minimal rationality, which means that rationality is not 100%, it is not non-existent, so you have a minimal rationality. And he also emphasizes trade-offs between cognitive constraints like short-term and long-term memory. So agents can compute everything. So rationality is bounded and selective. Not everybody is completely rational all the time, has access to everything in its memory. So Stalaker also is very important because of the concept of possible words. So he says agents can occupy multiple stable belief states simultaneously. Belief states are context dependent. Different possible words are activated in different situations. And so that's very interesting because I found this author from MIT also coincidentally. So he talks about logic and mathematics and how logic and mathematics can be modeled in part as the acquisition of information transfer abilities. So this is a quote from him. One can model an information transfer ability as the installation of a relation of accessibility amongst different fragments within the subject's cognitive states. So you have access to different belief states in logic and mathematics. So I was asking myself, can we do something like this, but not with logic and mathematics, but with probability and statistics? So this is why I think that I invented, I don't know, this term, fragmented statistical mind. So this is what I was talking about. Could a fragmented statistical mind be modeled? That's my question of my PhD. One that holds distinct belief states about scientific hypotheses and reasons probabilistic across multiple possible worlds. So I'm trying to work with probabilistic graphical models, which I'm beginning to study. So probabilistic, this is my hypothesis, that probabilistic graphical models provide a natural framework to represent such minds, handling conditional independence, local reasoning, and belief revision under uncertainty. And Markov chain Monte Carlo methods simulate the dynamics of such epistemic exploration. So this is what I'm going to do. This is very fast. I'm not a mathematician, not a computer scientist, not a physicist, and not a statistician. So I have to do these baby steps. I'm learning linear algebra, calculus. I learned a little bit, basic statistics. I'm starting also, and Python. So this is what I have to do. So this is my baby steps, and so I'm doing this so I can do an online course on probabilistic graphical models and to try to do this model with Bayesian networks, with propagation, and Monte Carlo Markov chain Monte Carlo methods. So why I'm doing this? Because I started to pay attention to the history of philosophy of Bayesian statistics, and I was trying to explain it in a structured way, and I thought that I couldn't do that with natural language the way Thomas Kuhn did it, to explain a structure of scientific, in his case, revolutions. So I was trying to see how the science evolves, particularly the history of statistics. So, just to show some history because this is very idiotic. So this is the main book that I read, and then read the articles inside of the book. This is the history very recently from 2011, from the brain, the theory that would never die, about Bayes' theorem and onwards. So I started here and started reading everything I could. And the problem is that my question is, I started to study Markov chain Monte Carlo because I think that it's a very fundamental thing for Bayesian statistics, and that's very. I'm going to talk about it, but my question is Monte Carlo Markov chain a scientific revolution in the way Thomas Kuhn refers to a revolution? So you have this is almost everyone knows it, but according to Thomas Kuhn and the structure of scientific revolutions, they involve paradigm shifts. So it's the replacement of one dominant scientific framework by another that is incompatible. Let's just stay here because I don't have too much time, because this is the most important thing about Kuhn's ideas. So let's keep just to the question of if Markov chain Monte Carlo is a revolution. So first, what is, not formulas, but explaining generally, what is Markov chain Monte Carlo? Markov chain Monte Carlo is a family of algorithms that use Markov chains to generate samples from complex probability distributions. It was developed at Los Alamos during World War II to estimate solutions to the Boltzmann equation in statistical physics. I just discovered it the other day because I'm not a physicist. I was very happy to see it. So, and Markov chain Monte Carlo simulates these distributions by walking through possible states, accepting moves with a probability that reflects energy differences. It was first formalized in 1953, so it's very recently. It was generalized by Hastings in 1970s, but it was just started to work properly with computation in the 1990s. So it's very recent thing. So everyone talks about Markov chain Monte Carlo being a scientific revolution. Almost. This is McGrain, this book, and she says this, almost quoting an article by Robert and Casella from 2011, around 2000, the same year, this book. And she says, almost instantaneously, Monte Carlo Markov chain and Gibbs sampling changed statisticians' entire method of attacking problems. In the words of Thomas Kuhn, it was a paradigm shift. Well, Thomas Kuhn wrote, so Thomas Kuhn wrote his book in the 60s. He had, I think, maybe no idea of this or didn't mention, I don't know, but my opinion is that so, in my opinion, in considering Thomas Kuhn's concept of scientific revolution, Markov chain Monte Carlo is not a revolution. And why it's not, I hope this works. This book is from econometrics, great, one page talking about Monte Carlo Markov chain methods. This is from the early 2000s, so maybe I'm too old and it's an old book. And here it's a book, introduction, a book about statistical inference, 3 pages on Bayesian statistics. So this is not a revolution because you have the majority of work with p-values in this theory. So this is not a revolution because it's not universally adopted. It's not a revolution. And everyone, and specialists in Markov chain Monte Carlo, say that it is a revolution. But I don't think it is. So I'm trying, I have just a few minutes and many slides. This is two examples of people that I want to model. So this is John Ioannidis, I hope I'm pronouncing closely. So the important thing about him is that he's a meta-researcher. So he studies things, if the scientific studies are true or not, and how good are they. So he's a Stanford professor also. So I'm going to skip this because I don't have time. Just to say that he has an article called, where is it? Something like, why most published findings are probably false. So this is a very cited article, and he says that the gold standard are never achieved and everything might be false, and he just explains why it is. And I used Google Colab to do a graph about what he says, and just to have a look of what I'm thinking. This is what he's thinking, and this is what I'm trying to do. This is not probabilistic graphical models, because there's no probabilities in these arrows, but just for example, we have a observed p-value, and the true hypothesis, and pre-study odds. This is going from one part, one node to another, until you come here, you have a post-study probability. This is base update. So I'm making frequencies Bayesian in my model. So that's I really like to do that. So we have prior probabilities, stereo probabilities, and then you have a transition, that is a concept that I'm trying to develop, and then you find the most probable hypothesis through Bayesian selection. So this is just to take a look at an idea of what I want to do. This is not perfect, and I'm still trying to, this is just a rough idea. So let's skip it. This is another statistical line that I think that I want to work with, trying to model. This is Robert Wiener. He's the founder of cybernetics. So, I'm going to quote him. Quicker. come back to Gibbs again, accidentally, not so accidentally. So, but all of these gaps theories, I am convinced Gibbs, rather than Einstein or Heisenberg or Planck, to whom we must attribute the first great revolution of the 20th century physics. Here I agree with the word revolution. So this revolution has had the effect that physics now no longer claims to deal with that what will always happen, but rather with what will happen with an overwhelming probability. This is the preface of this book on cybernetics. So this book is devoted to the impact of the Gibbsian point of view on modern life, both through the substantive changes it has made indirectly in our attitude to life in general. So he says, I repeat, Gibbs' innovation was to consider not one word, but all the words which had a theory that its probability is called entropy, and the characteristics tendency of entropy to increase. So this is my view. I think that I can model things in this framework, this Bayesian framework, or with many words, probabilities, entropy. So this is my almost last slide. So I'm composing this with a quote that I found in the same PhD thesis from the beginning, with the first quote from Toiber. And this is a mathematician. I haven't heard of him until a week ago, maybe. So, but I found this very interesting. He says, probability theory and statistical inference now emerge as better foundations for scientific models, especially those of the process of thinking and as essential ingredients of theoretical mathematics, even the foundation of mathematics itself. So I'm trying to do this structure of scientific thinking, meta-analysis, and things in a Bayesian way with this Gibbsian framework, something like this. And this is my final slide, finally. So just one slide. This is a possible PhD dimension still taking shape. The aim is to model probabilistic reasoning for science, individual, collective, theoretical, and my philosophical anchor, because I found some interesting things. It's very technical, of course, but even though there's some very philosophical, interesting things here in this so PhD thesis, namely probabilistic computation, and my claim is that philosophy of science must engage with the history of statistics, especially Bayesianism, and the rise of computational inference. Not a conclusion, but instead to probabilistic landscape of possible scientific words. So that's it.
Thank you, Maida. Brandon?
Super interesting project. I hate to add more to your reading list, which is already extensive, but there's a couple things that really are helpful for me. And so first, do you know about Clark Animore's book, The Mind's Arrow? He uses Bayes nets explicitly to model the mind. So that might be a nice, he gives a general overview of how you might model minds using Bayes nets. And then there's a really cool paper, this is a short one, by Brad Efron, about the history of empirical Bayes methods. It's my favorite. It's short. It's like 30 pages. It's relatively short. That's my favorite. It's a really interesting project, but I found those things to be helpful. So that's things here. Things that can be done.
So Daniel has a question. Then Walter, then.
So I've been reading about similar topics recently. And you mentioned Monte Carlo, Markov chain Monte Carlo methods and how they relate to thermodynamics, Boltzmann distribution. And there's a general concept called energy-based models. And I think it was last year that the Physics Nobel Prize was awarded to 2 computer scientists who developed algorithms that are based on this idea of energy-based models, Hopfield networks and restricted Boltzmann machines. And I think they use this Markov chain Monte Carlo method. And there's a bunch of energy-based modeling in AI. It's still not a big thing because I think they're still figuring out how to train it effectively and to make it efficient. But there's a bunch of leaders in the AI industry who are trying to make general intelligence partially based on energy-based models. So I think maybe it's going to be a revolution in the next 2 decades.
I also, I'm glad to hear something like this happening.
Right, I'd like to congratulate you, right, for this nice idea of coming here and presenting your possible project, to collecting information or criticism or good ideas or better reference. I think it's very nice, very good. I only do not think that the Monte Carlo and Markov chains are real revolutions because they are not in field. They are sort of new ideas on making up risk algorithms and so on. Should not be really a revolution, but that just does not care. It's not important. It's important that you are here collecting ideas or criticisms or even support for your perspective. Good.
Yes, I think
Well done.
about that because some people think it is, some people think it isn't. So this is a great question to discuss.
According to Kuhn's theory, a revolution embraces a theory, not a tendency or an algorithm or a method.
Yes. I'm still figuring out exactly what Markov chain Carlo is. So this is very recent. I'm still studying linear algebra and equation statistics. So I know that I already
Well, the scope of your presentation is broad, is very, very broad. Maybe too broad for a PhD thesis, but I will concentrate in a very specific topic. That's the topic that Walter commented, how revolutionary Monte Carlo methods are. I think it's a very interesting topic. And I will start my comments recalling a statement that Brandon made yesterday. You said, well, a good theory is a theory that does help you to do what you need to do. And he added a second part of that statement, with the resources that you have. I say that all the time. I use, instead of resources, I used to say with the means and methods that you have. You know that I'm a very strong critic of frequentist statistics. But a wonderful thing that we can say about frequentist statistics, that almost all the computations that I need to do in frequentist statistics, I can do it with a slide rule that has scales for the Gaussian distribution and the chi-square distribution, several degrees of freedom, and the G distribution, the F distribution, but a slide rule. One of my hobbies is to collect old calculation devices, slide rules, mechanical calculators, early electronic calculators, early personal computers, not mainframe computers, but early personal computers. Well, and Bayesian statistics, I have a professor that used to go to the very early congresses in Bayesian statistics, and he says the very first Bayesian statistics congress were very small. You could fit everyone in a small bus. Why? Because it was useless. Every Bayesian statistics model requires you to compute integrals that you cannot compute with a slide rule. with a mechanical calculator, or even with one of the earlier electronic calculators. You can compute those integrals with Monte Carlo methods, and you can implement Monte Carlo methods with the first programmable computers. And it's very interesting that one of the 4 first programs written for the ENIAC was a Monte Carlo simulator to compute neutron dynamics to build nuclear reactors and atomic bombs. One was a program for linear programming to select targets in war operations, there where the name of operations research comes from. One for solving ordinary differential equations to compute trajectories of bombs, and the fourth one I don't remember. But I would say Monte Carlo methods are revolutionary because they completely change the means and methods that are available for you to do science. And the consequence of this revolution was making Bayesian statistics mainstream. And then you think, what's Bayesian statistics? There are several definitions of what's Bayesian statistics. My definition of Bayesian statistics is, I say a Bayesian admits to talk about probability in the parameter space. For a frequentist, that's forbidden. But all modern frequentist statistics models talk about do Monte Carlo methods and implicitly are doing probability of operations in the parameter space. So the frequentists, the modern frequentists, are Bayesian without even knowing it. No? And they are this way because they use Monte Carlo methods, and that's why they can implement interesting large models. So I would say it is a revolutionary technique. And analyzing this topic, I would say, is enough for a very good PhD thesis.
Would you say it's a Kuhnian revolution?
Interesting question. It's a revolution. If it's a Kuhnian revolution or in which way it's a revolution, it's not that clear. That's why it's such a good topic for a PhD thesis.
But it is a break of paradigms. It leads to a break of paradigms. So it could be thought as a Kuhnian revolution, maybe.
I have to ask.
On account of breaking paradigms.
Thank you for your questions.
Martins from Federal Rural University of Rio de Janeiro. And he will finish this block with his presentation, Carnap's Confirmation Conundrum, Chasing Continuity in Probability.
Before I begin the presentation itself, I would like to thank the organizer of the Expo workshop itself and for the opportunity to talk about my initial research in the technology. Well, my speech on digital and explanatory process are the best, so I follow a written description whose slides as a guide, right? So basically the presentation will be divided in three main parts. First I will present the main question that guide this presentation. Follow that I will give an overview of Carnap's project, which you understand deductive logic as a form of simplification. I will also briefly comment on how this project evolved over the time. Well, next I will outline the main stage of Carnap's Bayesian theory of information. And finally, I hope, I will present some open challenges such as the epistemic equality of different C functions and the choice of lambda value. So, I will focus on two main questions. What would type size, what way does Carnap propose the selection of the most appropriate parameter this function within the framework of this theory of the logic? And how does this approach integrate the critical learning and account for the notions of inductive probability and partial entitlement? Well, Carnap's theory of inductive logic is changed in important ways, both in the formal sense and basic ideas. It's often said that Carnap moved from a logical view of probability to a more subjective one. In this view, it's not a just shift from one theory to another, but a change in how Carnap understood what he was trying to explain, this phenomenon of probability. To avoid extreme interpretations, and since Carnap project in inductive logic was continuous, I will say here partial non-subjectives. This weakens the idea that Carnap clearly supports objectivity based on Bayesian theory. So I will briefly analyze how Carnap's idea developed. For this, I will focus on Carnap's published ideas, especially in logical foundations of probability, the continuum of deductive methods, and the Shook collection. In this work, Carnap addressed deductive probability as a logical concept and sub-deductive logic as a way to provide explanations. He called this a rational explication. To follow how his ideas changed, we need to look at Carnap's two-part model of explication. The original vague idea, as used in everyday language or in scientific practice, the explicandum, which is a clear version of that idea, chosen for analysis, and the explicatum, which is the formal concept that takes the place of the original theory. My main point here is that Carnap's chance in the logic were mostly about the explicandum of probability, not the explicatum of the explicatum. So, a good place to start with Carnap's distinction between with Carnap's distinction between two kinds of probability. Probability one, which is a logical semantic concept, and probability two, which refers to real-world evidence. Carnap's deductive logic is focused on explaining probability one. So we have this outline of explanation problem. In this outline, CQ and C are predicate, not function itself. So in foundations, Carnap presents three approaches to explication of probability: degree of confirmation, parametric quotient, and estimates of relative frequency. On the other hand, in Shook, the preference shifts from the notion of degree of confirmation shifts from the notion of degree of confirmation to something closer to rational credibility. However, this problem remains the same. Credibility does not affect the internal part of the system. So, based on this process of explication, the system is logically built. Its rule defines a function based on ideas such as symmetry, regularity, and invariance. However, Carnap never claimed that these relations were objective semantic facts that exist independently of formal system. They are conventions. They are conventions adopted according to methodological tolerance. So the goal of inductive logic was not to describe objective truths, but to offer a useful tool for inductive reasoning. So the initial formalization of inductive logic in foundations ends with the definition of privileged confirmation function. In the continuum, Carnap offers a more flexible solution, parameterization of the space of the functions. This allows the selection of the function of best suit the specific purpose. In this way, we define a class of the functions that are equally valid or virtuous, instead of being correct functions. Inductive logic then comes to be seen as a continuum of methods, all logically valid, but different in their practical applications. The focus of this explication remains on the use of these functions, but this explication is becoming changed according to the project. So we can see that this choice is guided by a general framework selection scheme, which reflects the background of Carnap's meta-philosophy, as how it works like implicit, minimum synonymy, natural language, and empiricism, semantic ontology. This formalization or revisionist view brings inductive logic closer to the decision theory based on epistemology, while still preserving a semantic foundation. Inductive logic becomes a tool for guiding decisions where logical probability values are directly applied in rational choice. This becomes from the rest of the functions. The Carnap approach itself, the idea is fairly simple. With probability 1 in a meta-theoretical context, where probability is applied to naming of settings and events. This is done with a definition of homogeneous L, then specifying a sample space and epistemic perspective on the probability function. Basically, we follow 4 steps. Consider a probability function defined over L, define a relation between the set function and the probability function, define a conditional probability function by convention, and step 4, find the function to represent confirmation when there is none. Carnap in fact combines step 2 and 3. He assumes in foundation directly. Step 4 is where we observe the key difference between a general function and a continuous or lambda system, namely family of parameterized functions known as the continual inductive method. In Carnap's framework, step 3 involves identifying to a relative probability function that is a conditional probability based on a specific context or domain. Each domain corresponds to a state description, which is defined as a maximally specific conjunction of atomic or negative atomic sequence. Essentially, a complete specification of a possible word with the language. what matters at this stage is the range of the events and the range of the hypotheses across these state distributions. Right? So, if the range of evidence is a subset of the range of the hypothesis, then the hypothesis should be true. Thus, the greater the overlap between the range of evidence and the range of the hypothesis, the higher the probability that is hypothesis is true even the evidence. Now let's consider let's look at a simple language L. So we not select the language L merely for the sake of simplicity. It's also motivated by the technical challenges where this lambda system finds multiple argument predicates. Although L is a minimal language with only 2 individual quantities and 2 monadic predicates, it remains expressive enough for proposal. Moreover, despite its simplicity, we can enrich this language by introducing predicates by definition, chance, and meaning possibilities. In total, L admits exactly 16 state descriptions. Each state description contains a conjunction of Q predicates, that is the conjunction of mutually exclusive and exhaustive molecular predicates. Well, for instance, that is a state description over the language L. The range is defined by basically analogous of first order logic. Well, based on this, we are now in a minimum position to define a regular function which is based on a simple regular necessary function and for the range of the sentence. This function must be satisfied the following condition, very simple condition. Total. That's our quasi step 3 in the process. And we have the first definition. Since the intersection of the range of the evidence and the hypothesis is equivalent to the range of the conjunction, the interpretation of this ratio becomes clear. It expresses how much of the evidential range support the hypothesis. So, in addition to regular function, we also consider symmetric M functions and C functions. They are functions that assign the same value to all isomorphic state description. That is, descriptions that are structurally identical to a permutation of individual constants. Your language L, there are 10 isomorphic state descriptions. Well, this symmetry allows us to distinguish 3 important levels of description: structural description, a disjunction of all isomorphic state descriptions, individual distribution, a conjunction specifying which predicates apply to which individuals, and statistical distribution, a disjunction of isomorphic individual distribution expressed in absolute or relative variance. A simple that is. So, in step 4, we have 2 possible functions. C star is both regular and symmetry, and assign the same vector average structural description, or a stack or programmatic one. Is both regular and symmetry, and assign equal value to every individual state description. Basically, a valid part of indifference principle of Laplace. So, the function CDEP seems to be the natural choice for step 4, given the reasoning followed when merging step 2 and 3 in the first edition of formation. However, the problematic one has a significant limitation. It does not incorporate new information or experience. For instance, suppose we test pens to see whether they fail on the first attempt at an F. We conduct tests on pens P1, P2, P51. So, in the absence of any prior evidence, the evaluation is off. Now, imagine that the first 50 pens had all worked perfectly. We still obtain our value. So, given the limitation of TPO and the complexity of proceeding which C star in virtual language, a proposed solution to encompass learning by experience is to assign an explicit, quantifiable, and comparable parameter what will select the appropriate C function. Thus, the continuum or lambda system is a continuous family of C functions, each defined by a parameter value, lambda, which determines the relative weight between the empirical and logical factors in designating probabilities to a hypothesis based on evidence. The C lambda functions are particular case of C functions, being symmetry and based on regular distribution. They form the formal part of the function of inductive methods. We have the lambda system. The lambda system 4, right? Basically, the idea is that the degree of confirmation the next observed individual satisfies the predicate M, giving a history of observation represented by a individual distribution I. Here, M is defined by the disjunction of the W predicates. So how does this address the question of learning from experience? Well, if lambda equals 0, the function corresponds to a purely empirical inference, relying solely on the observed fragments. Otherwise, the function tends to be purely logical, designating probabilities based exclusively on the syntax structure of the language, that is, the PO. So if we particularly have lambda that depends upon the key, that is the number of keepers in our language. Suppose that lambda k will equal ck, where c is a constant. For example, say equal 1, we find so we have lambda kappa. We find the C sharp function, that is the equal value distribution of the structure description. Other example is for kappa, we take M with 2, let's S equal 10, and so S equal 1. So the value of the C lambda function changes for various choices of lambda value. For instance, if lambda equals 0, that is a purely empirical function, we have a value C lambda equals 0.1. If I have lambda well, 16, we have lambda equals I think it's that. Maybe I got some value wrong here because I only told about this in the lunch, so probably I take some mistake in calculus. So if you have lambda who tends to infinity, we have on 5 that is CPU, or Fourier logically the function. So basically that's the basic idea of the function. Of course, lambda occurs a positive part of real number. Right? So a key problem in Carnot's lambda system is how to shows of the value of lambda. He suggests that this choice should consider how well the method works in practice, how simple it is, and how elegant the result looks. However, he didn't give a clear specification for how to balance these different goals. Furthermore, he rejects TPO by introducing a new axiom saying that the function, the CDAC function, violate the second part of this axiom because it's the blighted numbers. So in practice, the best way to find the value of lambda is leftover. Well, I skipped the two alternatives. All alternatives is problematic if you accept the rational criteria proposed for calculus here. Only one method is admissible with TPO. But I speak about the disparity function. So what a little more about TPO as on its elements. This becomes even more interesting when we compare the lambda system with the disparity function or the delta system. Basically, a system based from a generalized principle of instantial relevance. Both systems converge when delta equals 0 and lambda tends to infinity. This happens because, apparently, if we take into account some common conditions like regularity, constants of unpredicated symmetry, negation invariance, and Johnson's sufficient postulate, it turns out one function satisfies all of them. And as is the TPO, the problematic one. In short, if we apply the principle of indifference to the finest part of the language, the natural way to divide the space when we have no evidence is through atomic state or state description. It seems that the best and intuitive solution we have is also the most problematic one. At this point, we come to the key idea. It seems that if we accept the proposed rational criteria, only one method is allowed, TPO. So, furthermore, two key ideas for theory of confirmation are inductive plausibility and partial entailment. The lambda system works well for the inductive plausibility when lambda is small. The confirmation function considers both the evidence we have and the logical part of the language. However, the lambda system cannot fully express partial entailment. And this happens because for low values of lambda, the result still depends on the evidence, not just on logic. Otherwise, when lambda tends to infinity, we have TPO. So because it ignores evidence completely, this option fails to reflect the inductive plausibility. Well, the problem is usually assigned to step 4, choosing a good function to represent confirmation when there is no evidence. If you use TPO, you are a purely logical inference. If you will use a lambda system, we don't know the way to choose the best lambda value of our proposal. However, the main problem could be in step 3, define conditional probability by conviction. The idea comes from an analogy with the bets, that the degree of belief in H given E is slightly far bet odds for H assuming E is true. However, this doesn't always work. There are at least 2 cases where the EDS break down, where when E is not a proposition expressible in the language of L, in which case we will have to make postulations about the meaning of E. So if we take it this way, we create a new language. So the probability is not the best of previous system. And when E is expressible but has zero probability in the absence of evidence. So what would be the way forward? Well, I have no idea, but an interesting way is to try a parameter close to TPO, or really should match the chance of us learning from the evidence among all probabilities. We should pick the ones that are as close as possible to total ignorance, and then follow a step-by-step process like the one on figure, showing figure 2, and based epistemology. For instance, the ideas of calibration or equivocation of beliefs, to find the best value of lambda. In this sense, the approach would be partially non-subjective. It would be subjective in intra-system, meaning there is one rational answer for each set of evidence, but it will still be subjective in this sense of creating and enrich the system itself. As logical values are, non-logical values are necessary for this process. Well, thanks everyone for hearing me in the reference.
Very much, Miguel. Now we're open to questions. Brandon? Thanks, Luca. I'm glad you talked about current. It's a great setup for what's coming up tomorrow. So I'm going to contrast what I'm doing current. So that was great. That saves me a lot of time. That was good. I appreciate it. Anyone else? Okay, so we can finish this block.
Okay, so now we begin the last block of today's presentation with Rodolfo. Rodolfo is a researcher here, Clip, and he will talk about some algebraic remarks on university. Okay, so Rodolfo, you can start.
Thank you. Good afternoon, everybody. I hope I am able to tell the tale in English. The first part, the most the talk will concern the prehistory, let's say, of the paper we published together, which appears there in the abstract. So this is prehistory, before meeting Brandon last year. Well, I suppose you know this very well. This is just a conditional fragment of Frege, 1879. It is duplicated and with a conditional prime, so we have two conditions. We call them, the first I will just say conditional, and the other one I will call it conditional prime. And here we have the same situation with Gensen. So we have the introduction and initial elimination group. Both of them duplicated. Okay? Well, I don't know when exactly, but I was interested in this question. It happens that here, in this context, in Gensen, if we assume one of the conditionals, then using here elimination, and just one more step, introduction. This is the one Gensen used to indicate, the ones we used to use to indicate that this is cancelled. One can, this way, prove this very easily. Let's write G for Gensen. Okay? So this is very easy, very straightforward, very natural. Just eliminating one conditional and introducing the other one. Okay? Well, something similar may be done with the other connectives in the Gensen world, meaning conjunction, disjunction, and negation. We could also mention bottom here. This depends on the language. It's not important for my talk. So we can prove. I will use the word. I will say that the conditional is univocal because this happens. If we duplicate the system, we can prove this thing on, of course, the other way around, because it's just inverted here the rules, and we'll get it the other way. Okay? This is enough.
Is this consequence variation the same for those or not?
For what?
Consequence variation.
Yes.
Is the same for two different implications or not?
I am assuming I have a system here where just take them as two connectives with these rules. I have just proved this here, this proves. So in this system, I have both conditionals. I have the conditional and the prime, both of them.
Yeah, no,
just
okay.
take them as two connectives.
My question is, if you have the same connectives in two different conditions, don't they define two different deductive relations or consequence relations?
There are no different conditions. They are the same. I'm just duplicating the introduction, the usual introduction and elimination. So the conditions are the same. Okay. Well, we do this in this case, and something similar may be done with these three connectives in the Gensen way. Okay? And it's also very natural, very straightforward, just introducing and eliminating one of them, eliminating one, introducing the other. We can do this sort of thing in these other cases as well. No problem. So the very natural question arises, what happens if instead of the natural deduction world, we are in the Frege world, where the usual conditional is given by this, the first two, as you very well know, and modus ponens, of course. So what I'm doing here, I'm duplicating the first schema, the second one, and also here modus ponens, everything twice. Okay? And I ask the same question. Now, in the Frege world, is this the case? Okay? Well, if you spend some 5 minutes trying to do this, you will sort of feel that something is it's not going to work. Okay? Just a suspicion, it's very natural. And everybody, after 5 minutes, trying to combine both conditionals, this is sort of very difficult to follow what's going on, but the natural suspicion is no. The answer will be no, okay? But that is not a proof. Okay. But then, as here we have the situation, we have mentioned the conditional, but I said that this is also the case with conjunction, disjunction, and negation. One may try to see what happens in the case of conjunction. Maybe in the case of conjunction, we are lucky and we can do it. Okay? Now there is the difference here, because in this case, conjunction, introduction, and elimination just need the connective conjunction. Here, the usual Frege way, we need the conditional. The conditional is sort of, I don't know how to say it in English, it's always needed in order to present the actions for the other connectors. For instance, in the case of conjunction, in this world, something we can do. Frege didn't do this because he was formalized in classical logic, and so he defines conjunction. But let's think we are in the intuitionistic world, and I want to introduce actions, schemas for conjunction. This is the usual way to introduce conjunction, and in order to eliminate, we have these two actions. Okay, so this is the basic system now. But what is the question now? Well, the question now will be just using this conditional, let's call it the basic one, and duplicating here conjunction. So I have to duplicate here the actions. I have to write this with the conjunction prime, and similarly for the elimination, conjunction prime. My question is the same. Is it the case that in this system, Frege system, from alpha, beta, I can arrive at alpha, beta prime? Okay? So, well, we can do this because it's not difficult. We want this, so as I usually teach when I teach logic, this is better understood this way. So I say, I want to get here. So what action gives me this one here? So I would say, well, I want that one. Because if I have that one, I will be able, I don't have it, but if I had this, I would be able to eliminate it somehow, because I would need alpha and beta. But alpha and beta, of course, are not difficult to get, because I can write this here, and also the same with beta. And so here I can eliminate this, the basic conditional, it's the only one I got here, and beta. And then I have alpha with modus ponens. I will get this formula with this here, and afterwards automatically eliminate this. Okay? So, perfect. I have proved what my question was whether this could be done. In Frege system, meaning just one conditional and just duplicating the actions schemas for conjunction. Okay? Okay, great. Question. Can we do this also for disjunction and negation in the vicinity world? Yes, it's completely similar. I wanted to just give this example, but it will work exactly the same for disjunction and negation. So what we have here is that having the conditional is very helpful here because we can prove the univocity of conjunction, disjunction, and negation. The only guy that the problem that remains is what happens when we just have the conditional. Okay? So I will forget about this. It's already proved. I don't want to confuse what here. Okay. So this is the question. What happens in this case? Well, this was a long time ago, and simultaneously I checked the bibliography. Maybe somebody has already said this question. Okay. So it's not immediate. We should check the bibliography. Well, this question, not this question exactly. I don't remember this question stated. I remember the general idea stated in different places, but not exactly this question. So it took me some time to do this, and I discovered it was this Italian, 1902. Apparently, I have to say, apparently, Padua of the piano school had stated. Let's say the general definition that's involved here. But I say apparently because I found it difficult to follow the paper. But afterwards, I find another paper, which I have already mentioned in some other occasion, logician from Romania, or Moisil, where he proves that the conditional is immutable. That he proves. He actually proves. First theorem of his paper. So I'm talking about Moisil 1942. What does he prove exactly? He proves this. Okay? So here is not the prime. The prime appears here. Not this. Let's say not the principles connected. But yeah.
If you accept both implications, do you have the deduction to both?
No. We don't have the deduction theorem in this system. It can actually very easily, it can be proved. I mean, our models prove this.
You don't have...
Oh no, because if both of them are together, we have a model. So the deduction theorem does not hold when we have both conditions.
Then with both conditions doesn't hold.
Oh, yeah. Well, one of them, yes, of course, because it's the usual situation. If both of them are together, we have models proving that this is not the case. Okay. Okay? Well, so Moisil apparently has solved the question because with the usual, if we have the usual monoponents, we can, of course, prove this. And this is exactly what we wanted to know. So he did it. But what are his conditions? His conditions is, I am adapting to the situation here, but it's the same. One of the conditionals is exactly this thing here. So the Frege fragment of the conditional, the usual two schemas and monoponents. This is, okay? his conditional. And what is this prime here? This prime here is not the duplication that I had given here. This prime is something different. It is as follows. It's given by the following action schema and the following rule. So this is the basic conditional, and this is the prime. So we have this action schema, which you can easily read as modus ponens as an action, okay, with the prime here. And we have this rule where we can think of this as introducing negation, okay? And this one as eliminating negation. Sorry, this is an action schema, I should have written this. Okay? So he's not doing this, he's not duplicating that. He's just taking the basic one, the same as we do, and then he's adding another connective, which satisfies this action schema and this rule. And in this situation, he proves this. Okay? Okay, he did that. So he is not answering the question. And I was curious to know what happens in the case of negation. He does something similar to what I have already done with conjunction. So when he handles negation, he proves univocity of negation, but he does exactly the same game, let's say, that I did when I wrote down the case of conjunction here. Okay? So he's sort of using two different notions. In one case, he does what I was doing all the time, and in the case of the conditional, probably because he was not able, he proceeded in a different way. Okay? So, well, the natural question arises, which would be the natural general definition of univocity. And it's the one we were using, okay? Which means just duplicate every action scheme and rule where the conditional to be tested for a univocity, duplicate it, and try to prove what I wrote down there. In the case of the conditional, whatever connected with this. I think this is very clear. Okay, so the problem was not solved by Moisille. So what do we do? Well, if we suspect that this is not the case, we will try to find a model. So, a model. Okay, I'm not very good at models. But so I did everything I could with deduction, and when I couldn't do anything else, I said, well, I have to go for models. Well, models. Models, yeah, I prefer to think in algebra. We have a universe which is not finite, and at least one element. Of course, we will not be able to do anything with one or two elements. Not possible. So we go for 3 elements. What can we do with 3 elements? Okay. We will try to prove that it doesn't follow. So, thinking in the usual way, we shall try to find an algebra, for instance, where this has value 1, and the other formula doesn't have value 1, and supposedly we can prove soundness and completeness. Soundness is enough. In fact, we are done. Okay. So, 3 elements. Well, I'm familiar with deterministic logic. So the first thing I will think on, right here. Three-element algebra, which is just one, which is given as follows. Okay. Not made a mistake. Let's take this as this guy. This is the usual 3-element Heyting algebra. But I don't have 2 3-element Heyting algebras. I don't have a Boolean three-element algebra that exists. So, but I shouldn't need a hiding algebra because here only this guy is involved. So I have to remember that Skolem, 1952, started studying Hilbert algebras, which are the natural algebraic counterpart in this case, only the condition. Okay? So the question is, no more time. Okay. So the question is there any other? This is also, of course, this is a hiding algebra. It would also be a Hilbert algebra. It happens that there is another Hilbert algebra of 3 elements, and we are lucky because this algebra behaves as follows. Why do I say we are lucky? Because of this. Okay, so we're done. It's proved that we have proved that this is not the case. Very easy. Okay, I have very little time. This would be the conditional prime. Should have taken more time to do this. Well, okay, problem solved. But then we have very natural problems in this context. For instance, this is just the trivial conditional. What happens if we add Peirce's rule here? Maybe this makes it stronger enough in order to prove that it is univocal. Or what happens if one also considers in intuitionistic logic, the action schemas for conjunction, for disjunction, and negation in any combination, maybe because all of them will use the conditional, maybe this makes the conditional stronger, and we will be able to prove that they are univocal in one of those cases. Okay? But these are many cases, and the connectives appear combined. It's not just the conditional, it's conditional with conjunction or with disjunction or in any combination. And so Brandon arrived last year with his programs. So it was brilliant, really. We were able then with Brandon to find all those models. All those models. And we were able to prove that there's only one combination where the conditional is univocal. Only one. Which is the combination when we have the Peirce conditional, meaning the usual actions, plus the usual Peirce schema. So everybody knows here. So adding, this is Peirce's law here. And adding the action schemas for disjunction, we can prove that the conditional is univocal. I will finish with this because it happens. The programs are very good in order to know yes/no answers, but when it comes to read, understand what's going on with the models, or understand a derivation by the program.
The original completely different.
How do you say conselho in English? My advice. Just take this information from the programs as saying yes or no. But don't lose time trying to understand or follow what's going on. Because this is incredible. You get programs, this size, and well, we tried to simplify it. I took the wrong way, which was try to understand the derivation. So I managed to simplify it, and this is what appears in the paper. That's the that simplification, very short. But this simplification is sort of ridiculous. I mean, so I will show a very natural and human and understandable, like human person with no problem, and I will end my talk derivation. How do we prove that the conditional is univocal in the first extension having disjunction? Okay? Well, I will write it down here. And you see, it will be very easy to understand because where it may be someone tries to understand what's written in the paper. So this is very well. I'm using 1 and 2 instead of. This is the way I've written here. It's the same. This is one of the conditions. Never mind which one because they are both the same. They're just duplicated. So we have this, which holds by pairs. Maybe you remember in the first extension, this is the second one. We can prove, if we have the usual first conditional and disjunction present, we will be able to prove this. And then this is basically all the work, because if I have alpha, this gives me beta. From here, I will be able very easily to get this guy here. Just substitute alpha for beta because this holds, and then well, this is just an action, of course. This is very immediate. I'm just writing here 2, 4. This is an action, of course, action schema, basically the first one for the second conditional, and a very well-known property, which is alpha implies alpha, instantiated with alpha implies beta here, which is this, everything with 2. And finally, using these 3, automatically we get alpha. So this is very easy to follow, anyone understand it. And I just managed to do this 2 weeks ago because I was sort of not too busy with other things.
But was suggested by the program, right?
Yes, the program, right, yes, the program. If someone has more time, the problem is one has to publish and all that. But here what's going on is that in first extension, disjunction is definable. So maybe you don't have that in mind here, but so if we are in the first extension, disjunction is definable as this formula here. So my suspicion is that the fact that in first extension this guy works as conjunction has something to do with this derivation. Okay, there are many problems, there are many questions, some I have answered and others have not, regarding where all those examples come from. I mean, if you see the paper, there are lots of tables, lots of algebras there involved. What are exactly those algebras? How can they be explained? Most of them I have found a way in order to understand. Otherwise, it's just tables. If you just have the table, what's going on? But there is a way to understand most, not every example, but most of the examples I was able to understand. I suppose I don't know.
We have little time for questions, but Brandon?
I just wanted to add, this was such an amazing experience. I didn't even know that any questions like this were open. But here's what was most shocking to me. Take Frege's complete system with implication and negation. That's the official system everyone uses when they're doing like meta theory of non-proof completeness. The conditional is not univocal, but you need a 6-element matrix to show it. And if you want to do a Boolean, you need an 8-element Boolean. And here's the mind-blowing thing. You can have two conditionals that are both the 8-element Boolean algebra. But one gets a designated value, the other doesn't. It's mind-blowing. It's absolutely mind-blowing. And when we sent this paper out to our referees, they're like, what? The conditional in the Begriffsschrift is ambiguous? It's kind of mind-blowing. So I thought this was a really fun project. Discovered without this recently, by the way. We'll talk about more of this on Friday, but without the tools, we wouldn't have discovered it. So.
No, very quick. I think this is fantastic work, but what are the implications for the Freudian philosophy for this point? I mean, I think this is the most important question we can do now.
We have I'm suggesting I get on that because I have a follow-up paper idea for this. Gensten was an inferentialist, and therefore it's important for him that the connectors have a unique meaning. That they are unique because he's an inferentialist. They're supposed to deliver the meaning. You can't do that in Frege. The conditional is not unique.
So this is a barrier for Frege's analysis.
This is a real problem. If you're an inferentialist, what it means is don't do it Frege Hilbert style because you don't get unique meanings for the connectors.
That's very important.
Yep. So we got to write a follow-up paper about inferentials and the consequences for it.
What's the relevant difference between the getting system and the axiomatic system that makes it arise? What makes this bizarre difference?
I don't know the complete answer to that, but one aspect for sure, I think, is that Gensen managed to separate the connectors. Managed to. This was in the spirit, if you see the papers of the 30s in Germany, Hilbert or Nice, and you see how the different axiomatizations go and change, you can easily perceive they are trying to separate the connectors. This is very natural, because if you have all of them together, you don't know what's going on. So you want to separate the connectors. And they managed to separate conjunction, disjunction, and negation. By conditional, no, because as you see, Frege, they still had this sort of axiomatization, and they used systematically the conditional in order to give the actions for conjunction, disjunction, and negation. So they are mixed. Okay? In the case of Gensen, no more of that. He managed with these two rules to separate the conditional from the others. And remaining rules, of course, as you know, conjunction, disjunction, negation. In the case of conjunction, just uses conjunction. In the case of disjunction, just uses disjunction. In the case of negation, maybe the formulation that uses also the bottom, but the bottom goes together with the negation. And you can, as Pravitz, just use negation, bottom if you want, or you can also just use negation if you want. This is just, I don't know exactly what is the reason why Gensen chose to have this sort of redundancy, because he has both negation and bottom, and one is enough. Okay? I think this is just, this is not very important. Some people have, I think, criticized from the relevant logic area that Gensen didn't separate the negation from the bottom. Okay? But in fact, you can do that. You can just give rules for negation without bottom. There's no problem. Maybe it's better in order to make, work with, to have both of them. But it's not that it's really necessary. So I think this more or less answers that question. Separate the connecting. Don't have them together, because otherwise it's confusing what's going on. What connected is responsible for what if they are together?
Okay, thank you very much.
Robert, did you know that Gerson died only with 33 years? He was an atheist. It's supposed that he went to the battle with the army, Hitler's army, and disappeared. Nobody knows when he died. Huh?
On the other side.
Fighting with
Good to have you.
33 years. That was
It's redundant, okay?
So now, let's continue with our program. And we have here Pedro Carrasqueira, which is a PhD here from Clay under supervision of Auto. And he will talk about the politics of the infinite.
Okay, thank you very much, Rafael. First of all, I'd like to apologize for interrupting for this presentation because I myself would very much like to continue the discussion, so but I have to present my own work, so yeah. So I'll be discussing with you guys some interesting problems in social choice theory. For those unfamiliar with social choice theory, a brief presentation of what it is. So social choice theory is essentially the mathematical study of collective decision making. Okay, so we can think of such situations, such things as elections, law, the market, even theory choice in science. These can all be seen as collective decision making phenomena. And in principle, we can use the methods of social choice theory to study them. But in this presentation, we'll focus exclusively on electoral procedures, okay? So we are in the context of democracy. So, a brief history of social choice theory. Marquis de Condorcet is considered the father of social choice theory. With his work on, well, he has two important works. One is about the so-called jury theorem. I won't be discussing that, but his refinement of so-called plurality voting, which is basically the voting rule that says that, well, we should accept as chosen by a collective society that candidate that has the most votes in an election, simply. Okay, but plurality voting has some problems. The main problem is that it's not stable in the sense that we have situations in which a candidate may win an election in the plurality voting, but we can see by checking counterfactual situations, removing candidates from the race, that in pairwise comparison, another candidate would win the election. So he's the strongest candidate in a sense. He's the so-called Condorcet winner of the election, but this is not the candidate that would be picked by plurality voting. So there's some sense in which plurality voting leads to some kind of unfairness. Okay, so in order to remedy that problem, Condorcet proposed we should move to so-called pairwise, okay, there's many names for this in the literature, but I'll be calling it pairwise majority voting, which is basically majority voting, but we should consider candidates disputing one against one and combine the resulting pairwise comparisons to get a ranking of the candidates considering the whole information obtained. Okay? So this is an improvement in the sense that we avoid that problem with plurality voting, but we get some different problems. The so-called Condorcet paradox. The Condorcet paradox means that there may be situations in which, well, we will have basically, well, this a candidate. It's better if I draw this. Okay, so we can get a candidate, let's say we have three here, A, B, C, and A should rank above B, B should rank above C, but C Okay, should rank the other way around. C should rank above A. So we have cycles, ranking cycles, because, well, we can have, as here in the example, we have three voters and three options, three candidates, and they're essentially the preferences regarding the candidates are, as you can see here in the example, they form a cycle, because one prefers A to B and B to C, two prefers C to A and to B, and three prefers B to C and C to A, so every option wins 2-1 against some other option. So we should have, according to pairwise majority voting, a situation like this. And in a situation like this, we don't have a winner. Okay? So, and I should make a caveat here, because we are reading the history of social choice theory backwards, because I'm starting with Bayes' theorem to get to Arrow's theorem. But in 1952, May proved the following. Actually, his proof isn't like exactly this one, but it's essentially the same. Okay, that pairwise majority voting is characterized by these properties. Okay, so what I'm calling here pairwise independence, it's usually called independence of irrelevant alternatives, but there are more than one condition called independence of irrelevant alternatives, so I'm here trying to specify the one that is relevant to this characteristic. Okay, so the idea is majority voting, pairwise majority voting, is the only social choice rule that satisfies all these conditions. Pairwise independence means that basically we should form the ranking only considering pairwise comparisons. Neutrality means that the options are all treated the same, essentially. Anonymity, the name is a little bad here, but it's the standard name. It means that all voters are treated the same. So essentially their identity doesn't matter. That's why anonymity. It has nothing to do with an epistemic notion. Okay, and positive responsiveness is there just for completion because I won't be interested in it. Okay, so we have a characterization of pairwise majority voting. So I'm proposing, it's important to notice, I was forgetting about this, pairwise majority voting has these consequences. It also satisfies these conditions, they are consequences of the other conditions. Condorcet consistency means that when we have a Condorcet winner, that's the one. It will be chosen. Okay? Unanimity means that the social ranking agrees with the voters' preferences whenever they all agree. If they all vote the same, that's what should be the social ranking. No questions about it. And non-dictatorship, the most important for our discussion, means that there is no voter who chooses alone. I mean, there is no voter that whatever he thinks should be the social ranking happens to be the social ranking. Okay, so he's not deciding alone. Okay, important observation, non-dictatorship is a weakening of anonymity, because anonymity has to do exactly with voters being treated the same. Of course, we have a dictator, they are not being treated the same. So, as we have seen, however, pairwise majority can guarantee the existence of a winner. So here's the problem, and as I said, I'm reading the history of social choice theory backwards because Arrow's theorem came before May's theorem, but I think this is a nice way of presenting it. Arrow's theorem as trying to answer a problem posed by May's theorem, which is this. Okay, so we have those conditions. Okay, if we are to get decisiveness in the sense that we always have a winner, or actually something stronger, that we always get a social ranking in the sense that we have a first, a second, etc., etc. Well, we need to, because that's majority voting, pairwise majority voting is the only social rule that is characterized by those conditions, we have to weaken some of the conditions, okay? So I'll be reading Arrow as posing the following question. Okay, so let's say we want a social ranking, but and suppose we assume the minimal democracy possible, which is basically this: unanimity and non-dictatorship. When everybody agrees, things are as everybody agrees, and we shouldn't have a dictator. The baseline democracy, let's say. Okay? And of course, he's also assuming pairwise independence because we want to bar that problem we had with plurality voting. So we're keeping that. Okay? So framing like this, well, what has Arrow found? That we simply can't get a rule that satisfies all these desiderata. Okay? So essentially, every social choice rule that is transitive in the sense that we have a ranking, and okay, it satisfies pairwise independence, unanimity, it's necessarily dictatorial. We have a dictator. Okay? Before we move on, we introduce two definitions because we will need it for the language. A coalition will mean a group of voters in a society, simply a set of voters. Okay? And we say a coalition is decisive if when everybody in that coalition agrees on how to rank two options, X and Y, then that's the social ranking. Okay, so they effectively, if they can all agree inside the coalition, that's what will be imposed for the whole of the society. Okay? So, and here's where things get interesting. Okay, all those conditions together, except of course non-dictatorship, they all imply that the collection of all the sides of coalitions in the society, they must form a neutral filter. I won't go into the technical details of what is a neutral filter. This doesn't matter for. I'm trying to keep this informal, but the definition is there. Okay, so the point is that Arrow implicitly assumes that in the proof of this theorem that a society with only finitely many voters. Okay, and for finitely many voters, it is well known. A neutral filter on a finite set is always principal. That is, we have basically we have a singleton set, and all the other sets in the filter are exactly its supersets. So this means, well, we have to have a singleton set with which is decisive, and this is the dictator. It's a group of one person who is decisive. It's a dictator. Okay. But the interesting thing is that, well, when we go to an infinite society, which is obviously an abstraction, we get the possibility of satisfying those conditions because, well, according to the ultrafilter theorem, or the ultrafilter lemma, which is a consequence of the axiom of choice, okay, infinite sets can have non-principal ultrafilters. Okay? And this is, I think, there are three papers which are in dispute for who is the author of this theorem, but I think Hanson came first, although his paper was published last, but all the other authors, Fischer and Kierman, and forgot the name of the other, well, they all have read his paper. It was circulating informally in the academy, so his paper is later, but everybody read it first, so I think he should be credited with the result. Okay? He has shown that given a non-principal ultrafilter, we can construct a social choice rule with the properties required by Arrow. Okay? So, well, what's the relevance of that? Okay, so we can satisfy it for an infinite society, but, well, given that we now can satisfy the errors conditions, we should ask, well, can we satisfy more conditions? I mean, is this the base? We only get the baseline. No, we actually don't get only the baseline. Actually, we can get almost all of the properties of the pairwise majority voting for an infinite society, with the exception of anonymity. Anonymity won't work because also, this is interesting, so the axiom of choice gets us a way of working around the conditions from arrow, but it will bar us, it's also the axiom of choice what will bar us from getting the whole of pairwise majority rule. Basically because, well, we will have, in an ultrafilter we should have either for complementary sets, we should have at least one of them should be in the, exactly one of them actually, must be in the ultrafilter, but we will have, it follows from the axiom of choice, we will have sets with the same cardinality, both it and its complement, and with the same cardinality of the original set. So this will imply that we can't, essentially we can't permutate the voters freely, because then we would confuse the sets. We should substitute one set for another in the decisive set of decisive coalitions. Okay. So I'll try to be brief. Well, so this is the setting for the question I want to pose. Okay, so why bother with infinite societies? Okay, there are some proposals in the literature. Mainly, Reiji Mihara has studied, interestingly studied, infinite societies. But mostly in the sense of, well, increasing the strength of the conditions and getting interesting ways of extending Arrow's theorem in some sense to the infinite. So mostly, I won't get into technical details, but mostly restricting the set of coalitions that can be accepted as decisive. So Reiji Mihara worked with computable sets, so trying to restrict the source of the ultrafilter. Okay, so I'm going in a different direction here. The direction I want to go is of asking the question, well, can this, in this form that I have presented, can this teach us anything about politics and democracy, even in the finite setting? Okay, so we are trying to, the idea here is, can we get some information about the finite setting from an infinite setting that is in principle practical, it shouldn't have any practical meaning, but it is, in a sense, an idealization which gives us some freedom. I was thinking a lot about Rafael's presentation yesterday, because I think we are trying to work with similar ideas here, that getting some room to accommodate some things and seeing where this leads us. Okay? And I want to suggest, and more like a pitch than a thesis I'm trying to defend here, but I want to suggest that, well, maybe this can help us by providing some kind of heuristics for solving real-world problems, as follows. So, for one thing, infinite societies reveal that Arrow's conditions and social choice rules are not inconsistent in an absolute sense, merely finitely so. So they are finitely inconsistent, but they are not inconsistent in the absolute sense. Moreover, they aren't absolutely inconsistent with the other conditions of majority rule, except with the exception of anonymity. Okay? Hence, And provided one has no qualms about the axiom of choice, because of course the axiom of choice is doing all the hard work here. Okay? In choosing to sacrifice from absolute democracy, the pairwise majority rule, understood here as the ideal of democracy, as representing formally what we mean by democracy here, in some sense, okay? In choosing what to sacrifice from democracy, we should try to accommodate for our conditions, or weaker versions of them, bearing in mind that anonymity has a different logical status than the other properties, because it's the one that is barred by the axiom of choice. Okay, so here's a suggestion of how this heuristics could be applied. Okay, suppose we're faced with the choice between two patches of pairwise majority rule. Okay, let's say both agree with it whenever it yields a transitive ranking for the given voter's preferences. Some cases, pairwise majority voting, pairwise majority rule works, so we don't mess with that, and we keep things as they are when it yields a Condorcet winner, even if we have, because we can have this kind of situation where we have okay, here's a winner, but okay, maybe there is dispute for second place. Okay, this doesn't matter. We have a Condorcet winner, so we keep it and we move on from that. Okay, but suppose we have a situation in which we have a cycle that prevents us from having a Condorcet winner. Okay, here is two ways of dealing with that. These aren't the only possible ways, but here are two ways I'm comparing of dealing with that. One is assigning the choice of the winner, in this case, to a selected voter. We could call it conditional dictator. Okay, so it goes to the Supreme Court to decide, things like that. Okay. While the other option is defaulting to a previously selected option, which will fail neutrality, okay? Because an option now is being privileged. Okay, so the suggestion here is that, well, given what we have seen about the infinite situation, about the logical status of the conditions, it seems to suggest that we should choose the first option. Why? Because that's the option that keeps neutrality but violates anonymity. Okay? And since anonymity can't be fully satisfied together with those other conditions of rationality by error, in principle, so we should give up anonymity, or should weaken anonymity in some sense. And this, I'm suggesting, this should be the reasonable way of solving most of democratic ruling, provided we don't have overriding reasons, because we may have overriding reasons in some cases. For instance, we are discussing perhaps constitutional reform, in which we have a privileged option because it's fixed by some previous social agreement, etc. So it's salient in some sense. So we may have overriding reasons. But I'm thinking here of maybe establishing society from nothing, like it's a free election, etc. We are not discussing these situations where we have salient options. Then I suggest, well, maybe the infinite case teaches us that in some sense this should be preferred. And I think there are practical reasons why this should be preferred, but this is what I wanted to present for this occasion. Okay, so this is the idea. Essentially exploring what impossible situations can teach us about possible situations. Thank you very much.
Thank you very much. Very interesting. So, you want to ask a question? Or?
Yeah, I mean, so only the action of choice can save democracy. Second, action of choice is independent. So democracy is independent. It independent from our choice.
Yeah.
Always. Right.
Yeah.
And the second observation, infinite societies are not so chimeric or impossible as they may seem to be, because you may think you are voting for the future.
Yeah.
Right? I mean, just a minute. And then if you vote for the future, the amount of voters is not limited. It can be increasing. So that is one possible way of understanding.
Yeah, I think Reiji Mihara has suggested some other possible ways. As I said, I was trying to restrict attention to these situations in which, well, the relevant society is clearly financed. So, in an election for president, etc. Okay, so.
Yeah, practically.
Yeah, whether we can learn something from the infinite, even in those situations. That's the question.
But then that makes Aristotle's theorem even more dangerous, because only the act of choice can save democracy.
Yeah, so that's another point I'd like to make. I mean, it's interesting how these things are connected to the action of choice. It seems to be playing a major role in those results, but well, we know the history of the action of choice, no problem. So this is interesting in itself. Yeah.
Brendan? I just clarification because I'm a little confused. So one thing that I thought was nice about majority reasoning was that the decisions supervene on the relative cardinality sets of votes.
Yeah.
That can't be true in the infinite.
Yeah, that can be true in the infinite.
So even if we had all the properties, quote unquote, of majority rule, it wouldn't be anything like majority.
Yeah, it wouldn't be. Of course, I'm abstracting from that.
So that's an interesting thing.
Yeah, that's an important point. Although essentially, what's going on here essentially is that, well, all finite societies are irrelevant in the infinite case. So essentially, we are getting some kind of infinite oligarchy. Yeah. Yeah.
But not composed of everyone. Just the odd people, odd numbers against the even numbers, right?
Yeah.
Oligarchy, but small.
Yeah, it's an interesting infinity, but
measure zero.
Yeah.
Right, so it's just interesting to think about what you go from relative cardinality to some other thing that's, even if you had all the properties, quote unquote, majority rule, but now in the infinite case, it's going to be some other feature of the comparative sets of votes that's decisive. It won't be the cardinality.
Yeah, it won't be the cardinality.
That's right.
Exactly. They all have to have the same cardinality. So that's interesting.
Makes no difference.
Counting vote, exactly.
Makes
It makes no difference, but we still can prove the properties. That's interesting. They seem to be related to numbers, but they aren't completely related to numbers. So I think because they are essentially, I don't know, they are principles of fairness. And when we apply them, they seem to be related to numbers, but they not necessarily. Okay, and Reiji Mihara has, I haven't read the paper, so I won't comment on it, but I know he has a paper on constructing social choice rules without the axiom of choice. So trying to revise the background set theory and see where it leads.
So is it known that you need choice specifically, or is it known exactly what the proof theory is trying to do?
As far as I can tell, there's very little, that's not very studied. So, because this involves a lot of, I mean, we need to keep the ultra-filter theorem, but we have to give up choice. So it's intermediate.
Yeah.
And this is very hard to study.
Yes.
Okay, so anyone else has questions? So, thank you, Pedro.
Thank you, guys.